There is a moon in our solar system that may have more liquid water than all of Earth's oceans combined. It orbits Jupiter, the largest planet in our solar system, a gas giant so massive that it contains more than twice the mass of all the other planets put together. The moon is smaller than our own, slightly smaller in fact. One of the quieter members of the extraordinary family of worlds that Jupiter holds in its gravitational embrace. From a distance, it appears almost featureless, a pale, slightly yellowish sphere, smoother than almost any other body in the solar system. Its surface crisscrossed by long, thin lines of reddish-brown that stretch for thousands of kilometers in every direction, like the cracked surface of a hard-boiled egg, or the veins on a leaf, or the fault lines of a world in slow and patient motion. That moon is Europa, and beneath its frozen surface, beneath an ice shell that may be 10 to 30 kilometers thick, there is almost certainly an ocean, a global, liquid water ocean, kept from freezing by the extraordinary tidal forces that Jupiter's immense gravity generates as Europa orbits. An ocean that has likely existed for billions of years. An ocean that, by every measure we apply to the question of habitability, has the characteristics that life as we know it requires. In recent years, the James Webb Space Telescope, that golden-mirrored marvel floating 1.5 million kilometers from Earth, turned its extraordinary instruments toward Europa, and what it found in the data it returned has deepened our understanding of this extraordinary world in ways that are, in the most careful and honest sense of the word, remarkable. Tonight we explore Europa, what it is, what lies beneath its ice, what Webb observed. Point 5. And what those observations mean for the oldest and most profound question that humanity has been asking since we first understood how large the cosmos is. Are we alone? We have the whole night to explore it. There is no hurry, there never was. As we begin our journey tonight, let us trace Europa's history, from its discovery to the gradual realization of what it might contain. Europa was discovered on the 7th of January 1610 by Galileo Galilei, using a telescope of his own construction. On that evening, Galileo observed 3 small points of light near Jupiter that he initially assumed were background stars. The following night, the points had moved, not relative to each other, but relative to Jupiter. On the third night, their positions had changed again. Galileo recognized what he was seeing. These were not background stars. They were objects orbiting Jupiter, moons, in the modern terminology, though that word was not yet in use in its astronomical sense. By January 13th, he had identified 4 such objects: Io, Europa, Ganymede, and Callisto. Together they are called the Galilean moons, and their discovery was among the most significant observations in the history of astronomy. The existence of objects clearly orbiting something other than Earth was a direct challenge to the prevailing cosmological model, the Ptolemaic, geocentric system in which everything in the heavens moved around Earth. Here were objects that demonstrably did not. Galileo understood the significance, and the discovery contributed to the intellectual revolution that Copernicus had set in motion. But in 1610, Europa was merely a point of light. Its nature, the ice, the ocean, the extraordinary internal structure, was entirely unknown and would remain so for 3.5 centuries. The transformation in our understanding came with the space age and the extraordinary missions that ventured outward to the outer solar system. The Pioneer and Voyager missions in the 1970s provided the first close images of Europa, revealing a surprisingly smooth, bright surface crossed by the distinctive linear features that would become its defining characteristic. But it was the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, that fundamentally changed our understanding of Europa and raised it, from a curiosity to one of the most scientifically compelling objects in the solar system. Let us explore how scientists concluded that Europa harbors a global liquid water ocean, because the case is built on multiple independent lines of evidence, each compelling on its own and together essentially conclusive. The first and perhaps most powerful line of evidence comes from measurements of Europa's magnetic field, made by the Galileo spacecraft during its repeated flybys of the Moon. Jupiter generates an enormous and dynamic magnetic field that sweeps through the Jovian system as the planet rotates. When Galileo measured the magnetic environment near Europa, it found that Europa generates an induced magnetic field, a magnetic response to Jupiter's changing field. This kind of induced magnetic field is a signature of a conducting material inside Europa responding to the changes in the external field. The most natural and most parsimonious explanation for such a conducting layer is a global ocean of salt water, salt dissolved in liquid water being, A5, an excellent electrical conductor, a layer of salty liquid water deep within Europa's interior, responding to Jupiter's rotating magnetic field like a secondary coil in a transformer. The magnetic evidence alone is powerful, but it is supported by the geology of the surface. Europa's surface is unlike any other in the solar system. It is extraordinarily smooth, smoother than any comparable body, suggesting that the surface has been continuously resurfaced and refreshed, with craters erased and topography smoothed in a way that implies the ice is mobile, even liquid, at depth. The linear features, the reddish-brown streaks that crisscross the surface, appear to be fractures in the ice shell. 5, where the ice has cracked open and new material has welled up from below, freezing in place and leaving the distinctive banded markings. The chaos terrain, regions where the surface appears to have been disrupted and refrozen in jumbled arrangements, suggests that at some point, relatively recently in geological terms, liquid water existed very close to the surface, disrupting the overlying ice before refreezing. The ocean is not merely theorized, its existence is written in the surface of the Moon for anyone with instruments sensitive enough to read it. As we continue our journey, let us understand the remarkable energy source that keeps Europa's ocean liquid, because without that energy source, point 5, the ocean would freeze, and Europa would be merely another cold, icy moon. Europa orbits Jupiter at a distance of approximately 670,000 kilometers, completing one orbit every 3.5 Earth days. This orbit keeps it perpetually in the grip of Jupiter's immense gravity. But Europa does not orbit alone. It is part of a gravitational resonance with two of its sibling moons, Io and Ganymede. For every orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise gravitational relationship, called the Laplace resonance, ensures that Io, Europa, 2-5, and Ganymede periodically align in ways that amplify the gravitational tugs they exert on one another. The consequence for Europa is that its orbit is kept slightly elliptical rather than perfectly circular. In an elliptical orbit, the distance between Europa and Jupiter varies. When Europa is closer to Jupiter, the gravitational pull is stronger. When it is further away, the pull is weaker. As Europa moves through its orbit, Jupiter's varying gravitational pull flexes the Moon, squeezing and stretching it rhythmically, like kneading dough with a powerful but invisible hand. This flexing, tidal flexing, generates heat through friction in the interior, rock grinding against rock, material deforming under stress. 5. The mechanical energy of gravitational interaction converting to thermal energy deep within the Moon. Spiegelfontein is the energy source that keeps Europa's ocean liquid. It is not solar energy. At Jupiter's distance from the Sun, 5, solar energy is approximately 25 times weaker than at Earth's distance, far too weak to maintain liquid water. It is not radiogenic heating alone. The decay of radioactive elements in the rocky interior, while contributing, is insufficient on its own. It is the gravitational energy of Jupiter and the Laplace resonance transmitted into Europa's interior as heat. 5. The same gravitational mechanism that makes Io the most volcanically active body in the solar system. Io is closer to Jupiter and experiences even more intense tidal heating, maintains Europa's ocean at liquid temperatures, possibly for billions of years. Let us build a picture of Europa's interior, the layered, complex structure that sits beneath the familiar cracked ice surface. Because understanding what Webb observed requires understanding the world it was observing. Europa is a differentiated body, meaning its material has separated by density, with denser materials sinking toward the center and lighter materials floating toward the surface. This differentiation occurred early in Europa's history, when the moon was warm enough that its interior was partially or fully molten. At the center, Europa has a metallic core, probably iron or iron sulfide, with a radius of approximately 500 to 600 kilometers. The magnetic induction signature measured by Galileo is consistent with a conductive core of this kind. Though the primary induction signal is attributed to the ocean rather than the core, surrounding the core is a rocky mantle of silicate material, similar in composition to Earth's mantle. This is the region where tidal heating is primarily generated, as the rock is flexed by Jupiter's gravitational influence. The interaction between the rocky mantle and the liquid water ocean above it is of particular scientific interest, for reasons we will explore shortly. Above the rocky mantle is the water layer, Europa's most remarkable and scientifically significant feature. The total depth of the water layer, including both the liquid ocean and the overlying ice shell, and 5 is estimated at approximately 80 to 170 kilometers. The liquid water ocean is thought to be approximately 60 to 150 kilometers deep, deeper than any ocean on Earth. Topping this extraordinary water layer is the ice shell, the frozen surface that we observe. Current estimates of ice shell thickness range from approximately 10 to 30 kilometers, though the uncertainty is considerable. The total volume of liquid water in Europa's ocean is estimated to be approximately 2 to 3 times the volume of all of Earth's oceans combined. 2 to 3 times all of Earth's oceans, on a moon smaller than our own, orbiting a planet 5 times further from the Sun. As we continue our exploration tonight, let us focus on what the James Webb Space Telescope has observed at Europa, and why its particular capabilities make it an especially valuable 5.5 instrument this distant world. Webb observes primarily in the infrared portion of the electromagnetic spectrum, wavelengths longer than visible light, 5 ranging from the near-infrared to the mid-infrared. This capability, combined with Webb's large mirror area and its stable thermal environment at the L2 point, makes it extraordinarily sensitive to the thermal and chemical properties of surfaces and atmospheres across the solar system. For Europa specifically, Webb's infrared sensitivity allows it to probe the chemical composition of the surface ice, identifying molecules by the characteristic wavelengths at which they absorb or emit infrared radiation. Different molecules leave distinctive fingerprints in the infrared spectrum. Water ice has one set of absorption features, carbon dioxide has another, sulfur compounds another still. By carefully analyzing the infrared spectrum of Europa's surface, Webb can identify which molecules are present, in what concentrations, and with what spatial distribution across the Moon's face. In 2023, a team of astronomers using Webb's near-infrared spectrograph and near-infrared camera published a significant finding from observations of Europa. The results were described in papers appearing in the journals Science and elsewhere, peer-reviewed, carefully analyzed, are 5 and striking in their implications. Webb detected carbon dioxide on Europa's surface. Carbon dioxide itself is not an unusual molecule. It is found in the atmospheres of Venus and Mars. It is present in many icy bodies in the outer solar system. Its detection on Europa is not, by itself, extraordinary. What is extraordinary on Europa's surface? The carbon dioxide was found, and what that location implies about where it came from. Let us examine the carbon dioxide discovery in the detail it deserves, because the significance of the finding lies not merely in the detection of the 5th molecule, but in its distribution and its probable origin. The carbon dioxide that Webb detected was not uniformly distributed across Europa's surface. It was concentrated in a specific region, a geologically young, disrupted area of the surface called Tara Regio, a chaos terrain characterized by the jumbled, five-eyed refrozen ice, typical of regions where the surface has been disrupted by processes originating from below. This spatial concentration is crucial. If the carbon dioxide had arrived from space, from meteoritic impacts, from the implantation of ions from Jupiter's magnetosphere, perhaps 5 from solar-wind interactions, it would be distributed more uniformly across the surface, or concentrated in patterns related to those external processes. Instead, it is concentrated in a region that geological analysis identifies as recently resurfaced and connected to the subsurface ocean. The most compelling interpretation, the one that the research team concluded was most consistent with the available data, is that the carbon dioxide originated in Europa's subsurface ocean and was delivered to the surface by geological processes. Material from the ocean, 5, containing dissolved carbon dioxide or carbon-bearing compounds. 5, was brought to the surface through the chaos terrain formation process and deposited there. This interpretation has profound implications. If carbon dioxide from the ocean is reaching the surface, it means there is active exchange between the interior ocean and the surface. The ocean is not sealed and static, isolated from the outside universe behind an impenetrable shell of ice. Material moves between the ocean and the surface. The two layers are connected. And crucially, carbon itself is one of the fundamental building blocks of life as we know it. Its presence in the ocean, in a form that suggests it has been transported to the surface, means that the chemical inventory of Europa's ocean includes carbon, 5 in an ocean of liquid water, kept warm by tidal energy. In contact with a rocky seafloor, the ingredients are assembling. As we continue, let us explore the requirements for life as we understand it. Because assessing Europa's habitability requires a clear framework for what life. 5. The requirements for life, as inferred from the only example we have. Life on Earth can be organized into 3 broad categories. The first is liquid water. Water is the universal solvent of biochemistry, the medium in which the chemical reactions of life occur, the fluid that transports nutrients and waste products, the medium that enables the complex molecular interactions that underlie metabolism, growth, and reproduction. Life, as we know it, cannot function without liquid water. 5. Everywhere on Earth where liquid water exists, including environments of extreme temperature, pressure, acidity, 5, and chemical hostility, life has been found. The second is an energy source. Life requires energy to maintain itself against the tendency of physical systems towards disorder, to build complex molecules, to drive chemical reactions, to sustain the processes of metabolism. On Earth's surface, the primary energy source for life is sunlight, captured by photosynthesis. But deep in Earth's oceans, at hydrothermal vents and cold seeps far beyond the reach of sunlight, life exists on chemical energy, the energy released by chemical reactions between warm, mineral-rich fluids and the cooler ocean water. This chemolithotrophic life requires no sunlight at all. The third is chemistry, specifically, the availability of the elements and compounds that the building blocks of life are made from: carbon, hydrogen, nitrogen, oxygen, phosphorus, 5, and sulfur. The CH-NOPS elements are the primary constituents of biological molecules. These elements must be available in forms that living systems can access and use. For life to build itself, Europa, by every measure we can apply, appears to satisfy all 3 requirements. It has liquid water, an ocean that may have persisted for billions of years. It has energy, both tidal heating and potentially chemical energy at the seafloor, where the rocky mantle contacts the ocean. And Webb's carbon dioxide detection adds to the evidence that it has the chemistry. Let us explore the analogy between Europa's ocean and one of the most extraordinary environments on Earth, the hydrothermal vent systems of the deep ocean, because this analogy is central to understanding why scientists take Europa's potential for life so seriously. In 1977, the research submersible Alvin dove to the Galapagos Rift on the floor of the Pacific Ocean and discovered something that fundamentally changed our understanding of life's possibilities. At a depth of approximately 2,400 meters, in the cold, lightless abyss where no scientist had expected anything remarkable, the researchers found thriving communities of life clustered around vents in the seafloor where superheated, mineral-rich water was being expelled from the interior. These hydrothermal vent communities were unlike anything previously known. The base of the food chain was not plants using sunlight, but bacteria and archaea using hydrogen sulfide and other chemicals, a process called chemosynthesis. These microorganisms were in turn the food source for tube worms up to 2 meters long, giant clams, mussels, crabs, and fish. Entire ecosystems sustained not by sunlight but by the chemical energy of the Earth's interior. Subsequent exploration has revealed hydrothermal vent systems across the floors of the world's oceans. Life has been found in the most extreme conditions. Temperatures at the vent openings exceeding 400 degrees Celsius, 0.5 pressures hundreds of times greater than at sea level, chemical environments that would be toxic to surface life. The significance for Europa is direct. If life can thrive on Earth at hydrothermal vents, sustained by chemical energy alone, in the complete absence of sunlight, then the question of whether life could exist in Europa's ocean becomes not whether the environment is capable of supporting it, but whether life arose there in the first place. Europa's rocky seafloor, in contact with the liquid ocean above it, bar 5, is thought likely to have hydrothermal activity driven by tidal heating. The interaction of warm, 0.5 mineral-rich fluid from the rock with the cooler ocean water above is precisely the environment in which Earth's hydrothermal vent communities thrive. The deep ocean of Europa may be the most Earth-like environment in the solar system outside of Earth itself. Not at the surface is a radiation-bathed frozen wasteland. But deep below, in the dark and warm ocean floor, the conditions may not be so different from the environments where some scientists believe life on Earth first arose. As we continue our journey through Europa tonight, let us turn our attention back to the surface, the frozen interface between the ocean world below and the space environment above, and explore what 5 it records about the processes happening beneath. Europa's surface is young, in geological terms. 5 impact craters, which accumulate on planetary surfaces over time and are used as a measure of surface age, are rare on Europa. Statistical comparison with the cratering record on other Jovian moons suggests that Europa's surface is approximately 40 to 90 million years old. The solar system is 4.5 billion years old. Europa's surface has been resurfaced on average many times over the age of the solar system. This young surface is itself evidence for the dynamic internal processes driven by tidal heating. Heat from the interior drives the convection of the ice, which resurfaces it. 5. Geological activity, driven by tidal flexing, fractures the ice and introduces new material from below. The surface we see today is not ancient. It is the most recent episode in a continuous process of renewal that has been running for billions of years. The linear features, those distinctive reddish-brown streaks that first caught astronomers' attention, are called lineae, and they come in several types. The double ridges, 2 parallel raised lines separated by a trough, are among the most common surface features. They are thought to form when the ice shell is fractured and material from below infiltrates the crack, freezing in place and pushing up ridges on either side. The process may be similar, in some ways, to the spreading ridges at the bottom of Earth's oceans, where tectonic plates pull apart and new seafloor material wells up from below. The reddish-brown color of the lineae, one of Europa's most recognizable features, is not yet fully explained. The coloring agent is most likely a mixture of salts and organic compounds that have been brought up from the ocean interior and modified by radiation from Jupiter's magnetosphere at the surface. Sodium chloride, ordinary table salt, has been identified as a likely component. Sulfur compounds from Io's volcanic activity, implanted by Jupiter's magnetic field, may also contribute. The surface of Europa is a chemical record of the ocean beneath it. Consider one of the most extraordinary and most debated features of Europa, the possibility that it erupts water vapor plumes from its interior into space. In 2012, the Hubble Space Telescope detected what appeared to be plumes of water vapor above Europa's surface, jets of material being expelled from the Moon's interior into the space around it. Subsequent Hubble observations in 2016 detected similar features, with the plumes appearing to originate from specific regions of the surface. The implications of plume activity, if confirmed, are profound. By 5, it would mean that material from Europa's ocean is being actively ejected into space, that the ocean is venting directly into the environment around the Moon. A spacecraft flying through such a plume could, in principle, sample the chemistry of Europa's ocean without ever needing to penetrate the ice shell. The plumes have proven difficult to confirm definitively. Not every observation of Europa detects them. They appear to be intermittent, present in some observations and absent in others. Their reality has been questioned and debated within the scientific community. However, the analysis of Galileo spacecraft data, observations made during Europa flybys more than 2 decades ago, has provided retrospective evidence for 5. Careful reanalysis of Galileo's magnetometer data from a 1997 flyby showed signatures consistent with the spacecraft having flown through a plume of water vapor and ionized particles. The signatures were not recognized as plume evidence at the time. 5. But in the context of subsequent Hubble observations, they take on a new interpretation. The balance of evidence suggests that Europa does experience episodic plume activity, that it is, at least sometimes, 5 venting material from its interior. Whether those plumes reach sufficient altitude to be sampled by a passing spacecraft remains to be determined by direct observation. NASA's Europa Clipper mission, launched in October 2024, is designed in part to search for and characterize plume activity during its many flybys of Europa. If plumes exist and Clipper flies through them, the chemistry of Europa's ocean may be accessible without drilling through kilometers of ice. As we continue, let us consider the environment that surrounds Europa, because it is one of the most hostile in the solar system, and it shapes everything about how Europa's surface chemistry operates. Jupiter is not merely a massive planet. It is a vast generator of charged particle radiation. The planet's powerful magnetic field, the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's magnetic field, traps electrons and ions in radiation belts that dwarf those of Earth. Jupiter's radiation belts are among the most intense radiation environments in the solar system, outside the Sun itself. Europa orbits well within these radiation belts. The radiation dose at Europa's surface is approximately 500 rems per day, a level that would be lethal to a human being in approximately 1.5 days of unprotected exposure. The surface is continuously bombarded by high-energy electrons and ions accelerated by Jupiter's magnetic field. This radiation environment has 2 significant effects on Europa's surface chemistry. First, it continuously processes and modifies the surface materials, breaking molecular bonds, creating new chemical species. Fine planting ions from the Jovian magnetosphere into the surface ice. The reddish-brown coloring of the Linnean chaos terrain is partly a consequence of this radiation processing. Second, 5. The radiation may actually contribute to the habitability of the subsurface ocean through a somewhat counterintuitive mechanism. As radiation breaks water molecules at the surface into hydrogen and oxygen, and as oxidizing compounds like hydrogen peroxide and sulfate ions are created by this radiation chemistry, these compounds may be delivered to the ocean through the cycling of surface materials into the interior. The ocean below the ice is thought to be reducing in character, low in oxygen, rich in materials from the rocky seafloor. The surface, irradiated by Jupiter's particles, becomes oxidizing. If oxidizing compounds from the surface are cycled into the reducing ocean interior, a chemical gradient is created. And chemical gradients are energy sources that life can exploit. Jupiter's radiation, so hostile to the surface, may paradoxically be one of the energy sources that powers life in the depths. Let us explore the chemical signatures of Europa's surface in more detail, particularly the evidence for salt, because the type of salt present carries direct implications for the origin of the surface material and its relationship to the ocean. Sodium chloride, the same salt that seasons Earth's oceans and sits on kitchen tables, was identified on Europa's surface through analysis of our 5 Hubble Space Telescope spectral data. The detection was made possible by observing Europa at ultraviolet wavelengths. Sodium chloride has subtle but detectable spectral features in the 0.5 ultraviolet that were identified in regions of the surface that had been geologically active. The significance of sodium chloride is that it is not expected to be deposited on Europa's surface from external sources. The Jovian magnetosphere implants sulfur-bearing ions from Io's volcanic activity, and various other compounds arrive from space. But sodium chloride is not among them in significant quantities. The most natural explanation for the presence of sodium chloride on Europa's surface is that it came from below, from the ocean. If Europa's ocean is a saltwater ocean, as the magnetic induction measurements suggest, and if material from that ocean is cycled to the surface through the chaos terrain and other geological processes, then surface salt is exactly what we would expect to find. The salt on Europa's surface may be dried ocean water, ancient brine, carried to the surface from a global ocean below, frozen and irradiated by Jupiter's particles until its original color and form are altered, but still detectable by the careful spectral analysis of 5 a space telescope. The surface of Europa may be littered with the evaporite deposits of an ocean that has been cycling material to its frozen exterior for billions of years. What other ocean chemistry does that surface record? What else has the ocean left behind in the eons of its existence? These are questions that future missions, particularly the Europa Clipper, are designed to begin answering. As we return to the central finding of Webb's observations, let us explore why the detection of carbon dioxide specifically, rather than simply any molecule, carries such particular significance for the 5 question of life. Carbon is the foundation of biochemistry as we understand it. It is the backbone of every organic molecule, every amino acid, every nucleotide, every lipid, every protein. The reason carbon occupies this central role is its extraordinary chemical versatility. A carbon atom can form stable bonds with 4 other atoms, the 5 simultaneously, including other carbon atoms, allowing the construction of molecules of almost unlimited complexity. The diversity of organic chemistry, the science of carbon-containing molecules, is, in terms of the number of possible compounds, 5 vastly greater than the chemistry of any other element. Life, as it exists on Earth, has exploited this diversity to build the extraordinarily complex molecular machinery of biology. For life to exist in Europa's ocean, carbon must be present in a biologically accessible form. Carbon dioxide, CO2, is one of the most fundamental carbon-bearing molecules. On Earth, it is a starting material for photosynthesis. It dissolves in water to form carbonic acid, which dissociates into bicarbonate and carbonate ions. In hydrothermal systems, carbon dioxide participates in the chemistry that forms organic molecules, including, under some conditions, 0.5 amino acids and other biological precursors. The detection of carbon dioxide on Europa's surface, apparently originating from the subsurface ocean, tells us that carbon is present in the ocean in a reactive, dissolved form, not locked up in inert minerals, not sequestered in a form that chemistry cannot access, but dissolved in the water, available for chemical reactions. Carbon, in liquid water, 5 warmed by tidal energy. In contact with rock, the inventory of habitability requirements continues to fill in. Let us examine what the abundance of carbon dioxide that Webb detected implies about the processes operating in Europa's ocean and interior. The carbon dioxide was detected at concentrations suggesting a meaningful source, not merely traces of carbon dioxide created by radiation, process icing of the surface ice, but an amount that implies a more substantial origin. The concentration in Tara Regio, the chaos terrain where the detection was made, was sufficient to be clearly identified and mapped spatially by Webb's infrared spectrograph. Estimating the actual concentration of carbon dioxide in Europa's ocean from surface detections involves significant uncertainty. The relationship between ocean concentration and surface abundance depends on the efficiency of the geological processes that deliver ocean material to the surface. 5. The rate of radiation processing that modifies the surface material, and other factors that are not yet well constrained. But the detection points toward a carbon-bearing ocean, and the specific location in recently resurfaced chaos terrain suggests active delivery of ocean material to the surface. Not ancient deposits from some past episode, but relatively recent, ongoing material exchange. There is a deeper implication worth considering. Carbon dioxide dissolved in water participates in what is called the carbonate-silicate cycle, a long-term geochemical feedback mechanism that on Earth helps regulate the planet's climate over geological timescales. In this cycle, carbon dioxide dissolved in water reacts with silicate rocks, weathering them and sequestering carbon. In Earth's case, volcanic activity returns carbon to the atmosphere. The cycle keeps Earth's carbon budget in approximate balance over billions of years. In Europa's ocean, a similar geochemical cycle may operate. Carbon dioxide from the water reacting with the silicate rocks of the seafloor, sequestering carbon in minerals, while tidal heating and geological activity return carbon to the water column. Such a cycle, maintained over billions of years, could create a chemically active and dynamic ocean environment, one in which the chemistry is not static but continuously evolving. Dynamic chemistry, changing chemical gradients, energy flowing through the system. These are the characteristics of environments where life thrives. As we continue our exploration tonight, let us allow ourselves to carefully, scientifically imagine what life in Europa's ocean might look like. If it exists, life in Europa's ocean, were it to exist, would almost certainly be microbial, not complex multicellular life, not fish or crustaceans or anything resembling the diversity of Earth's oceans. The energetics and the chemistry of Europa's ocean, while potentially supporting life, are thought to be relatively sparse in comparison to Earth's sunlit oceans. The energy budget is limited. The conditions favor organisms that are efficient, small, and metabolically flexible. The most likely life forms would be analogous to Earth's chemolithotrophs, organisms that derive energy from chemical reactions rather than sunlight. In Earth's hydrothermal vent environments, the primary energy sources for chemolithotrophs include hydrogen produced by the reaction of seawater with hot rock, hydrogen sulfide from volcanic activity, and methane. In Europa's ocean, the available chemical energy sources would depend on the specific chemistry of the ocean and the seafloor, potentially including hydrogen from serpentinization reactions, reduced sulfur compounds, and the oxidants delivered from the surface through ice cycling. These organisms would likely be extremophiles, not because Europa's conditions are extreme by universal standards, 5, but because they are extreme by the standards of Earth's familiar surface environments. Cold, dark, high pressure, with chemical energy as the only energy source. These are conditions that would be lethal to most surface life, but are essentially the home environment of Earth's deep hydrothermal vent communities. If life exists in Europa's ocean, 5, it has had approximately 4 billion years to develop and diversify. Earth's microbial life has had approximately the same time, 5, and over that period has developed an extraordinary diversity of metabolic strategies, genetic complexity, and adaptive capacity. Europa's life, if it exists, has had the same time to explore its own adaptive possibilities. What it has become in 4 billion years of dark, warm, 5 chemically rich ocean is one of the most tantalizing unknowns in all of science. Consider what it would truly mean, in the deepest scientific and philosophical sense, if life were found in Europa's ocean. The most significant thing about such a discovery would not be the discovery of life itself, as extraordinary as that would be. It would be the implication of independent origin. Life on Earth arose approximately 3.8 to 4 billion years ago from chemistry. The first living cells emerged from the organic chemistry of the early Earth, through processes that are still not fully understood but that involved the self-organization of complex molecules in aqueous environments. Every living thing on Earth, every bacterium, every plant, every animal, every fungus, every archaea, traces its ancestry back to that original emergence. We know of only one origin of life in the universe. One data point: if life were found in Europa's ocean, and if that life were demonstrated to be biologically independent of Earth life. Not contamination from Earth-launched spacecraft, not a related lineage that arrived via meteorite, but genuinely independently evolved biochemistry, then the number of known origins of life in the universe would double from 1 to 2. And from that single additional data point, an extraordinary statistical inference becomes available. If life arose independently in two places in a single solar system, on Earth and on Europa, then the emergence of life from chemistry must be a robust, readily occurring process in environments where the basic requirements are met. Life must be common, vastly common, perhaps ubiquitous, wherever liquid water and chemical energy and the right elements are available. The universe would look different after that discovery. Not just the solar system, but every solar system, every star with a habitable zone, every icy moon with a subsurface ocean, every body, anywhere, with the conditions that life requires, would carry a non-zero and perhaps quite substantial probability of being inhabited. Two independent origins of life in one solar system. The implications would cascade through every aspect of our understanding of the cosmos. As we continue, let us consider the mission that has already been launched and is currently traveling toward Europa, the Europa Clipper, the most sophisticated planetary science spacecraft NASA has ever built. Europa Clipper was launched on October 14, 2024, atop a SpaceX Falcon Heavy rocket from Kennedy Space Center in Florida. It is currently en route to the Jupiter system, following a trajectory that will take it on a gravity-assist flyby of Mars in 2025. A flyby of Earth in 2026, and arrival at Jupiter in April 2030. The spacecraft's design reflects the particular constraints of the Europa environment. 5. Rather than orbiting Europa directly, which would expose it to Jupiter's intense radiation belts continuously, rapidly degrading its electronics, Clipper will orbit Jupiter and make approximately 50 close flybys of Europa over the course of its primary mission. Each flyby will last only hours. 5. During which the spacecraft's instruments will collect as much data as possible before Clipper exits the intense radiation environment of Europa's vicinity. The scientific payload is comprehensive and specifically designed for Europa's anticipated properties. A radar sounder will probe the ice shell. 5. Potentially mapping its thickness and internal structure and searching for pockets of liquid water near the surface. A magnetometer and plasma instrument will characterize Europa's induced magnetic field with far greater precision than Galileo achieved, constraining the depth and salinity of the ocean. Mass spectrometers will analyze the composition of Europa's tenuous atmosphere and any plume material that the spacecraft encounters. Camera systems will image the surface in detail, mapping geological features and searching for evidence of recent activity. And the spacecraft carries instruments specifically designed to search for biosignatures, molecular indicators of biological activity in the 5. Surface material and any plume ejector. Webb has already told us something fundamental about Europa's chemistry. The 5. Clipper will spend years interrogating that chemistry in detail that no Earth-based or Earth-orbiting telescope can match. Let us explore what the Europa Clipper mission will be able to determine that Webb's observations, for all their power, cannot, because the two observational approaches are complementary in ways that together build a more complete picture. Webb observes Europa from Earth orbit, 1.5 million kilometers from Earth, but still vastly further from Europa than any spacecraft in the Jovian system. At the distances involved, Webb cannot achieve the spatial resolution to distinguish features smaller than hundreds of kilometers on Europa's surface. It observes the globally integrated spectrum of the surface, the average of all the chemistry across the face of the Moon. Europa Clipper, flying within 25 kilometers of Europa's surface during some of its closest flybys, Mite 5 will be able to resolve features as small as tens of meters. It will map the surface chemistry at a spatial resolution that reveals individual geological features, individual chaos terrain regions, but 5 individual lineae, individual impact craters. The spatial distribution of carbon dioxide and other molecules detected by Webb will be mapped in detail that reveals which specific geological processes are responsible for delivering ocean material to the surface. Clipper's radar sounder will probe beneath the surface, something Webb cannot do at all. The radar will send pulses of radio waves into the ice shell and listen for reflections from internal structures. If there are pockets of liquid water or briny ice near the surface, potential conduits connecting the ocean to the surface, the radar may detect 5 them. The thickness of the ice shell, currently uncertain by a factor of several, may be constrained. Most importantly, if Europa's plumes are active during Clipper's flybys, the spacecraft's mass spectrometers will analyze their composition directly. Not from hundreds of millions of kilometers away, through the integrated spectrum of a distant moon, but by flying through the plume material itself, collecting molecules and measuring their masses, identifying organic compounds, searching for the molecular signatures of biological chemistry. Webb opened a window. Clipper will step through it. As we move toward the conclusion of our journey tonight, let us sit with the philosophical weight of what we have been exploring, because the significance of Webb's Europa findings goes beyond the specific molecules detected. Webb has found carbon in Europa's ocean. Not speculatively, the carbon dioxide on the surface, concentrated in geologically active regions, points with considerable confidence to a carbon-bearing ocean. 5. Combined with the magnetic evidence for a liquid ocean, the thermal evidence for tidal heating, 5. The geological evidence for surface ocean material exchange, and the chemical evidence for salt, we now have, in the case of Europa, 5. A world that satisfies the known requirements for life more completely than any other body in the solar system besides Earth. That statement carries weight. For most of human history, the question of whether life exists elsewhere in the universe was purely philosophical. There was no scientific method for addressing it. The existence of other worlds was debated. The conditions required for life were unknown. The tools to observe distant worlds simply did not exist. Now, for the first time in the history of science, we are in a position to ask the question, empirically, to design experiments that could actually detect evidence of life beyond Earth. B5. To build and launch spacecraft that will fly through the material of another world's ocean and search for biosignatures. To use space telescopes to read the chemistry of distant worlds from hundreds of millions of kilometers away. We are the first generation of human beings with the tools to begin answering the question, rather than merely asking it. 5. Webb's detection of carbon dioxide on Europa is not the answer. 5. It is the deepening of the question, the accumulation of evidence that makes the question sharper, more focused, more urgent. It is the universe, through our instruments, becoming increasingly specific about where to look, and so we arrive, gently and without hurry. At the end of our journey tonight, we have traveled far together. From Europa's discovery in 1610, a point of light near Jupiter, seen through Galileo's modest telescope. 5. Recognized as something orbiting not the Earth, but another world, to the extraordinary scientific picture we have assembled over 4 centuries of observation and 4 decades of spacecraft exploration. We have stood at the edge of a world with a global ocean of liquid water, kept from freezing, not by sunlight, but by the gravitational embrace of the largest planet in the solar system. We have explored the tidal heating that powers that ocean, the fractured ice surface that records its dynamics, the induced magnetic field that betrays its conducting, salty nature. We have examined what Webb found, Carbon dioxide on Europa's surface, concentrated in regions of recent geological activity, pointing with considerable confidence to an ocean that contains dissolved carbon. Carbon, 5 in liquid water, sustained by tidal energy, in contact with rock that may host the chemical reactions of hydrothermal vents. In an ocean that has likely existed for billions of years, we have considered the implications for life, the deep sea analogy, the chemolithotroph communities of Earth's hydrothermal vents, the possibility that something has been living in Europa's dark ocean for as long as life has been living on Earth's surface. We have followed the Europa Clipper on its journey toward Jupiter, already traveling through the solar system, carrying the instruments that will interrogate Europa's chemistry in detail that no Earth-based telescope can match. And we have sat with what all of this means, not merely scientifically, but philosophically, that for the first time in human history, we have a world in our own solar system that satisfies the known requirements for life, and a spacecraft on its way to search for it. There is a word that is often used in this context, disturbing, and it deserves a moment of examination here at the end of our journey. The findings are not disturbing in the way that word is ordinarily used. They are not alarming. They do not indicate danger. They do not threaten. What they disturb is something deeper and more important. They disturb the comfortable assumption that we are alone, that Earth is not merely a special world, but the only world where anything interesting has happened. They disturb the ordinary human tendency to treat the cosmos as a backdrop to the human story, rather than a story in its own right. And they disturb, gently, productively, in the way that the best science always does, the certainty that the most profound questions are already answered. Beneath the cracked, irradiated, reddish-brown ice of a small moon orbiting a gas giant 5 times further from the sun than we are, there is an ocean, a dark, warm, liquid ocean, full of salt and carbon, resting on a rocky floor that may be exhaling warm, mineral-rich water into the cold water above it. An ocean that has been there for billions of years, in conditions that life on Earth would find familiar in their deepest forms. We do not know if anything lives there. We may know, within decades, what the data from Europa Clipper reveals. We may know what the next generation of missions, perhaps a lander, perhaps a cryobot that melts through the ice, finds in the water itself. But we do not know tonight. And in that not knowing, in that genuine, scientifically grounded openness, there is something extraordinary. The universe has not yet told us its answer to the most important question we have ever asked. It is still keeping the secret. Tonight, as you rest, somewhere in the dark beyond Jupiter, further than you can see with your eyes, beyond all but the most powerful telescopes, moving steadily in its 3.5-day orbit, Europa is turning in the light of a distant sun. Its ice is fractured and reddish-brown at the surface, glowing faintly with reflected sunlight, 25 times weaker than what warms us here. Jupiter hangs immense in its sky, striped and enormous, its gravitational hand flexing the moon's interior with every orbit. And beneath the ice, in the dark, in the warm, in the chemical richness of a global ocean that has been patient for longer than complex life has existed on Earth, something may be happening. Something that does not know about us. Something that has no way of knowing that from a small planet in the inner solar system, creatures made of atoms forged in ancient stars have built instruments capable of detecting the chemistry of its world. Something that has been there, perhaps, since before the first cell divided in Earth's young ocean, or perhaps nothing, perhaps just the water, 5 and the rock, and the patient chemistry of a world that has all the ingredients but has not yet, or perhaps has never, assembled them into life. We will find it out. Rest now in that extraordinary uncertainty. In the knowledge that the question is real, the search is underway. 5, and the universe may be about to answer. The ocean beneath the ice has kept its secret for 4 billion years. It will not keep it forever. Thank you for exploring with us tonight. May your rest be as deep as Europa's ocean and as full of quiet, patient possibility.